starting into magnetics, right? Give me 1 second. I'm going to try. Wait until this auto focuses, then I'm going to shut this up. Now this is. All right, I'm assuming everybody can see that okay then? The pad right here?
Yep, we're good.
All right, so any questions at all? Nothing?
I don't got any.
What I wanted to do is talk about, we're in chapter 3, and we're talking about magnetic fields. And I mentioned last time the differential H field. This is in your book, but I'm just going to put down that if you have a current element, you do this. If you have a current element that's simply IDL, and you're at a distance R away, and I'm going to use capital R here, that's a vector, and it's pointing from the actual current element to the actual point of observation, the H field, and you want the differential H field caused by that. And I'll even call R, AR here as a unit vector that points from the current element to the point where you want to observe the differential H field. The differential H field is given by I dl. Now that's a magnitude of I, and dl is a differential unit vector. And it's going to be IDL crossed AR. So it's crossed into this unit vector over 4 pi, and it's R magnitude squared. This is one way of writing it, and I'm trying to make sure with this little illustration that you understand which each component is. You all with me on this? Now, it is similar. Is your screen going off and on or not?
No, it's good. It's been fine for me.
Mine is, and I don't know if it's the power or what, but anyway, give me 1 second. There's something weird going on here. Let's hope that fixes it. All right, anyway. Now this one. What in the world? I give up. All right. So, all right. Next thing I want to do is say, if we talk about AR here, the unit vector AR, it's equal to sorry. It's equal to vector R over magnitude of R. So this equation can be rewritten, and this is the easiest way to think of it. Just put down IDL and then cross it into R. And down here, 4 pi, and just take R down here cubed. So this is where the vector is R. Here it is as well. This is a magnitude cube. Can everybody follow me on this, class?
Yep.
All right, next. Next thing I'm going to do is I'm going to do the classic problem. So I don't know what page this is on. There's 2 classic problems, an application of this. So the first problem I'm going to do is the easiest one. Let's say I have a loop, and if you can tell me what page this is on in the book, I'll be grateful. So it's a loop of wire. This is sort of the classic illustration. We got a loop of wire, and it's got a radius of A, and I'm going to assume a current of I is circulating around the loop. Call this the Z-axis, call this X, and call this Y. And I assume you can all see that and understand what the coordinates are.
Yeah.
And again, we're assuming the current's flowing this way. So suppose we want to find the differential H field at a height z. Let me use this marker. So I want the H field right here. Actually, the H field, but first the differential H field at a height z. Can you all follow me on this, class?
Yep.
All right. Now, the way we do it, you got to start somewhere. So you start on the outer edge of the loop at any point, and you're going to say there's going to be a given, say right here, there's a given IDL. Now, it's important you get this right always. I is a magnitude. We're going to assume it's the same everywhere in the loop. It's not going to be a function of azimuth. Azimuth would be this measurement phi. So it's I. Now, DL is important. Remember, this is something at a constant radial distance. So when we get a d phi, really, your actual movement here is going to be the wiper arm length, or it will be A times d phi, and it's going to be in the A phi direction. Now, does that make sense to everybody? A is the radius, A times d phi is the differential length, A phi is the differential direction. You all follow me? Can you see it, Chase? I see you, but I don't know if you can see it.
Yes, sir, I can see it.
I just want to make sure everybody can see it. I see, I've got Chase, I can see Zach, your name, you got it as Grays, but
Whoops.
it's fine. Anyway, I want to make sure everybody can see it. I'm assuming you can. So after you have that, now the next thing you need is this vector R. So you want to go from this point to here, and you want a vector that points this way, from the actual current causing the H field to the point of observation of the H field. Y'all with me, class?
Yep.
All right, what is that R going to be? Well, we'll do it in cylindrical coordinates, and there's an ambiguity here with azimuth. But first of all, I'm going to start with the difference in radial distance. What's the radius at the point of observation, class, if you're on the z-axis?
0.
0, right. It's 0 minus the radial distance here. I'll put it this way. It's 0 minus the radial distance here, which is A, right? And it's going to be in the AR direction, plus the z coordinate here is just z. The z coordinate here, it's in the xy plane, is 0. So it's ZAZ, right? And here's where d phi loses meaning. If you're on the axis and you talk about what phi it is, it makes no sense. There is no phi. Y'all follow me?
Yeah.
All right, but I'll show you how we can even insert that information. But first, let me get this. So our vector here is equal to minus AR plus ZAZ. And I'll tell you what he does in his book. That's R. What's the magnitude of R? Anybody? Isn't this a right triangle here? Z, R, right?
Yeah.
What is it? It's going to be, I should say a rho. In his book, he'll have rho. I use different books, but it's the cylindrical radial coordinate here. We'll call it a rho, right? I'm sorry, I called it R, but you all follow me, I hope. So the magnitude is going to be square root of this plus this. So it's the square root of A squared plus Z squared. I hope that makes sense to everybody.
Yeah.
All right, finally, after that, now I'm going to go ahead and get I'm going to set up the vector or the differential vector. So I get DH itself. Come on. DH will be equal to, and here it's going to be IDL. Well, I d phi, and there's an A here. So it's A d phi times I, and I is just the magnitude. It's in the A phi direction. It's crossed into vector R. I'm going to use this one. Maybe I can zoom that just a little bit for you guys. All right. So I'm using this port. My gosh, it keeps going out on me over here. And it has to be a loose connection. I figure out where. Give me 1 second.
Everything looks pretty good on our side. I can see everything pretty clear. I don't know about everyone else, but
Yeah. It's fine.
My screen's flickering. That's what I'm trying to deal with there. And I'm not sure the reason for it. I have a feeling it has to do with a plug. So Oh, a second. Oops. Hopefully I'll do it. Oh, guys. I don't know. Anyway, I'm going to keep working no matter what. So this is R vector here, and R is this vector. So it's minus A rho here, and it's going to be plus ZAZ. Then it's divided by 4 pi magnitude of R cubed. So that's the square root of A squared plus Z squared cubed would really be A squared plus Z squared to the 3/2 power. Now, are you all with me on this? This is D.
Yep.
Can you all follow me? Here's the one thing I want to mention. All right, we're going to do the cross product, then I'm going to talk about using symmetry. Then I'll show you how to break it down even without symmetry and get the right answer. So here, if you go ahead and do the cross product, first I'm going to take all the constants out in front for DH. So here I have AI, those two, over 4 pi. Now you'll notice that A squared plus Z squared at that point of observation never change. They are not a function of the position of the current. So I can take those out in front too. So I have A squared plus Z squared to the 3/2 power right there. Now I have to go through and do the crosses. Well, I have A phi crossed A rho. And what is that? Think about it. We got A phi, right? And it's crossed into A rho. Remember how to do these cross products? So it's A rho. I'm sorry, A phi crossed into A rho. It would be minus AZ, wouldn't it? Y'all follow me, class?
Yep.
All right, so it's minus wait a second. Yeah, that's right. But there's a minus here. So I'm going to say this. All right, so A phi cross A rho is minus AZ with the minus is plus AZ. And I'll just put it as AAZ. I mean plus AZ right here, because there's a minus here. Do you all follow me on this? I'm just trying to make sure here I take care of this. Then I have A phi crossed AZ, which is A rho, right? So it's going to be plus ZA rho. I'm trying to just do this part of the cross right here. And there's a D phi I'll leave out in front. Now, can everybody follow me on this?
Yeah.
Take a moment. I know it's not the cleanest thing, but you can follow me what I'm doing. Now here's the deal. Wentworth's book, he's going to say this A row component here, there's a differential d phi, and it's times A times Z times A row. Well, this right here is actually going to cancel if you do an integration from 0 to 2 pi. Technically, I'm going to flip this in a second, but technically we're going to integrate this from phi equals 0 to 2 pi. So if we integrate this from 0 to 2 pi here, his argument is going to be this A row term, because A row is pointing in the radial direction up here. Each A row term, there would be an A row term here. There'll be another A row term at the opposite side, equal magnitude, opposite directions, and they'll cancel. Now, this is Wentworth's argument. By arguments of symmetry, there is no radial component there. And that should make somewhat a fair amount of sense to everybody. Does that make sense to everybody? Let me get myself in there.
Yeah.
Okay. So next, right in front of the camera. Next, after that, when you do the integration, I'm going to just take this and move to the next page. When I do the integration right here, I get the technical integral would be h itself will be equal to an integral, and I'm going to take the constants out front, IA over 4 pi, and then it's going to be a squared plus z squared to the 3/2 power. Now, when I do the integration over z, it goes from az d phi, and that's this portion right here. I don't know if you can see it. I'm just doing this portion right here. I've got d phi. I took ai out in front. It's from 0 to 2 pi. That will give me a term in the az direction. Now this term right here plus z times the integral of a row, and it's d phi from 0 to 2 pi. The mistake people make is they'll say, well, that's 2 pi a row. You can't do that integral this way, because a row on the z-axis is it's ambiguous. Same with phi. So what you actually have to do is say a row itself. He doesn't do this in this book, but I'm going to show you this. A row can be rendered. If you think about what a row is, this is x, and this is y. And we have a unit vector here, a row, at some angle phi. Then the actual a row can be rendered. It's got a magnitude of 1, is simply equal to the cosine of phi ax plus the sine of phi ay. Can you all see what I've done there, class?
Yeah.
Some of you remember this from before. Well, if that's a row, and I just look at this portion of the integral right here, right, I can see that I'm integrating. Really, I have cosine of phi ax d phi from 0 to 2 pi. And I also have an integral from 0 to 2 pi of sine of phi ay d phi. Both of these are 0. Now, that's not even using an argument of symmetry. It's using the mathematics to prove the point. That means this component does not add anything to the integration. Y'all follow me?
Yeah.
For the H field on the z-axis, it doesn't. So what is the H field on the z-axis? And this is the beautiful thing about this. When we come back to this integration right here, since that goes away, it's just this. But what is the integral of d phi from 0 to 2 pi? Just 2 pi. If you agree with that?
Yeah.
So if that's 2 pi, you can see that this integration, or therefore the H field, and the only thing I'm doing is rewriting this right here with 2 pi a on top, becomes the H field on the z-axis. This is for a loop of radius a. I'll just put down loop radius equal to a. This is going to be equal to, there'll be an I a squared. If you find it in your book, tell me where this is. Over, and now the 2 pi and 4 pi cancel, and I get a 2 down here, and I get a squared plus z squared, and this is to the 3/2 power downstairs, and it's in the az direction. So that would be the H field on the z-axis from a current loop of a radius A. Does everybody follow me on this one?
Yeah.
Got some questions for you. So just looking at this, what's the value of where's the H field of maximum? Can anybody tell me?
At 0.
Right, at z equals 0. It's a maximum. What is it? Well, it's a squared over 2a cubed, right? Or it's I over 2a amps per meter in the AZ direction. Do you all see that? Everybody?
Yeah.
What does it go to at infinity as z goes to infinity?
Goes to 0.
Absolutely. Goes to 0. As a matter of fact, there's one last point about this. The H field is always pointing upward in the z-axis. It's only a function of how the current is rotating. If the current is rotating counterclockwise looking down the z-axis, the H field is in the positive z direction. If it's rotating counterclockwise, it's in the minus z direction. And here's how you get it. Now, there are varieties of the right-hand rule, but this is the easiest. Everybody has a right hand, right? I think. Hopefully here. Even though there are people that have fought in wars that don't. But anyway, I'm assuming everybody does. So take your right hand, grasp the current, or grasp that current loop, and have your finger on your right hand, your index finger, pointing in the direction of the current. When you grab it, your thumb will point in the direction of the H field. It's going the positive z direction. You all see that? If it's the other direction, if the current's going counterclockwise, it's negative z. Follow me, class? It's straightforward. There's nothing tricky. All right. Having said that, next. So that's the H field from a single. By the way, what if you had two loops of wire that, say you use insulated wire, shellac wire on top of each other? What would the H field be on the z-axis? The loops are on top of each other. One loop, two loop, both with a current I. They are 2 times the H field.
Just double it. Yeah.
3 loops, 3 times. 4.
Triple it.
As long as they're tightly wound, you can assume the distance variation is infinitesimal. And that's basically why coils of wire, I mean, there's more to this, but you got a bunch of coils of wire. You get a very much enhanced H field, even though there's the same current causing, the same current itself's going through it. That's not quite true because it can be a whole lot of turns, but this is the idea. Okay, that's for that one. Next, we're going to do the infinite lines. Now, remember, do you all recall the parallels? Remember when we had a loop of charge, what the E field was? The difference is the E field goes to 0 at the origin for a loop of charge, right? Here, the H field's a maximum. And the other thing is, for a loop of charge, same type of integral, there's no cross product. And I'll try to contrast these things. Do you at least have an idea what I'm talking about there?
Yeah.
Next, let's see. So after that, the next thing we do is go ahead and now we're going to do a long wire. An infinitely long wire. So if you have a very long wire on the z-axis, and it's got a current I, just assume you got a current I up and down the z-axis, and it's infinite. Look, it doesn't have to be infinitely long, but I'm going to start with infinitely long. This way it'll make sense. And I come out a distance rho from here. That's a right angle. And I want to know what the H field is here. That's what my goal is. Y'all follow me?
Yep.
So we're going to use cylindrical coordinates. And here, it's a multicolored thing. I'm going to start down here and I'm going to say if I have a current right here, that's going to be good. If I have a current here, little differential current, right? And it's going to be IDL here. Well, IDL would actually be equal to IDZ AZ. Right there. It has to have a magnitude and direction for the differential length. Can y'all follow me on this, class?
Yep.
All right. Now, if that's the case, trying to do this, trying to get out of that light thing, but I might not be able to. All right. So if that's the case right here, and I want this, we got IDL. Next thing we need is R. What is the radius vector going to be? Always think about we're in cylindrical. Point of observation minus the point you came from in terms of the coordinate parameters. So here the point of observation is rho. What's rho on the z-axis?
0.
0. So it's really just rho A rho plus what's the difference in z? This is at 0, right? And this is at z. I've drawn it so it looks like it's negative, but it's really this coordinate, 0, minus this coordinate. So technically it's minus z a z. Do you all get that?
Yep.
Now, here's where phi loses meaning again. I'm on the z-axis. Phi has no meaning. You're at a point here, it could be any phi, doesn't matter. Phi, the actual phi coordinate of this point and this point has nothing to do with the magnitude of that distance vector, but it does have to do with the sense, the pointing, what direction AR is pointing. Because if you think about AR like this pen. I hope you can see the pen right here. Well, if this is pointing and it's got an R component and a Z component, as it rotates, you can see the Z component will always be the same, but the radial component will vary over 0 to 2 pi. So the pointing sense of it changes. Now, I'll get to this in a second. So the next thing we do is write the differential H field. And we say the differential H field would be equal to IDL. Well, it's I. DL here is equal to DZ in the AZ direction. Crossed into R, or you could do AR, but R. So that's crossed into rho A phi. That's going to be minus ZAZ. We'll get to this in a second. It's all over 4 pi. And it's this value. It's the magnitude of this to the third power. So the magnitude is rho squared plus z squared to the square root to the third power means it's going to be equal to rho squared plus z squared to the 3/2 power. That's the differential H field. Y'all with me on this?
Yep.
All right. Let's do the cross product and we'll talk about the final result. DH, well, now you can see that z is going to change. You're going to do the differential integration with respect to z. So I can't pull this outside, but I can get I and 4 pi outside. Now what's left inside? Well, I have AZ, right? Crossed into A rho, and remember, it's rho phi z. These are positive, right? So if I have AZ crossed into A rho, it's going to be A phi. Y'all follow me on that?
Yep.
So that means it's rho A phi right here, and it's going to be in DZ. And then the next part is AZ crossed in AZ is, class?
0.
0. So that goes away. And we take that, and we've got rho squared plus z squared to the 3/2 power. And that, I don't know, it's in your book somewhere. If you can find it, let me know where it is. All right, so we take this and we integrate it from minus infinity to infinity. Technically, we could go from minus L over 2 to L over 2. We could do this and break it down. I'm not sure if I want me to do it that way, but when you go from infinity to infinity and do this integration as such, you're going to get the H field at a distance rho away is equal to I over 2 pi. And this is rho magnitude here. So I call it magnitude of rho. And it's in the A phi direction. But I have to make mention of what A phi is. A phi itself, this is important. A phi is going to be equal to AI, a unit vector in the direction of I, crossed into AR, a unit vector pointing from where the current is, the current element, or I should say the direction of the current element to the, and it's a unit vector here. Now, the reason I'm saying that, and I'm going to get to this in a second, I want you to pay attention to this point. First, you follow me? When you do this integration, you're actually going to get z over the over rho squared plus e squared to the 1/2 power, and then you evaluate it from plus to minus infinity, and it boils down to this. This is in your book. Is this formula 3/8 in your book? Can you tell me? Or not?
It's 4/8. It's on page
Sorry,
216.
My bad. 4/8. Problem 4/8. I have an old book I'm looking at right now. So it's my July 4th cup, red, white, and true blue. Anyway, our mug. If you take a look at this right here, this makes perfect sense that the current's on the z-axis. But what if it's not on the z-axis and you still have an infinite current? Now I want you to pay attention. So suppose I'm just going to say if it's an infinite current, the H field is equal to I, and it's just equal to I A phi over 2 pi, and it's rho. Here, rho is the magnitude from the axis of the infinite current to the point of observation. But suppose I have this. I want you to listen to me. Suppose I have this. This is going to be X, and this is Y, and this is Z. Now hear me. Now I'm going to say I have an infinite current, but it's in the Y direction. So I have a current I, infinite in the Y direction. And I want to know what the H field is at a point out here. We'll call it at a point 2, 0, 0. So at X equals 2, remember this is on the Y-axis, Y equals 0 and Z equals 0. So technically it would be down here, but I showed it here. I could say Y is 2 as well. Suppose it's 2, 2, 2, and I want to know what the H field is here. So how do you get that? Now pay attention. Well, you still use this formula because it's infinite. Here you're going to have the H field at this point at 2, 2, 0 will be equal to I. I'll just call it I. It doesn't matter what the value is. Over 2 pi. Now, what's the distance from here to here? It's got to be the shortest distance to the actual axis of the infinite current, class?
2.
Just 2. That's right. Now, my trick is getting A phi, right? So A phi in this one is going to be equal to di, and I'll put it down here. It's equal to, AI, unit vector in the direction of current crossed into unit vector, and I'll call it in the direction, the radial direction to the point of observation, A rho. So for me, AI is AY. Y'all follow me why it's AY, class?
Yeah.
It's crossed in A rho. What would A rho be? Has to be in a vector, class.
X.
AX, right? AX, right? All right, you do the cross product. It's minus,
AZ.
right. Now, how else could you get it? Remember I told you the right-hand rule business. You use this all the time. If you take, hear me now, your right hand, put it in the direction of the current, your fingers curl around in the direction of the H field on your right hand side. Technically, if the current's this way going out, my fingers curl around. Come right here and look. Right here, you see how it's pointing down? Put your right hand in the direction. You with me on that, class?
Yeah.
All right. What about if I was straight above it? If I was up a distance 2 in the Z direction?
Saying magnitude in the minus A or in the plus AX direction.
That's right. That's right. Right? What about out here? Now I'm still distance 2, but it's going to be at x equals minus 2. Almost looks like a swastika if you keep going with this. You with me? But it's important that you guys have an appreciation for how to do it. Ready? Now, what about this one? Here's the killer. Suppose I want the H field, but I want it at, again, for this thing where the current's on the Z-axis, I want it at the point 2, 2 is equals, I'm sorry, H at 2, 2, 2. Now how do you do it? Well, just where is this point 2, 2, 2? All right, well, here's 2 in the X, right? 2 in the Y would come up 2, right? With me? And I'm sorry, 2 in the Z would be that way, and 2 in the Y would be over here, but the Y component will not be a factor. I could do it over here and come up, right? And this would be the point, right? Y'all follow me? Y will not have anything to do with this. So how do you get this? Well, it's still going to be I over 2 pi. Now, what's rho? Here, I'm going to look right down the y-axis, and this is going to be z, and this would be x. So think about it. I've got 2 over, 2 up. Here's my point, right? That's 2, 2, 2. Correct, class?
Yeah.
What's this vector? What is rho right here? If you're measuring, well, actually, measuring from the axis. Rho itself would be what? Well, it's going to be 2ax, right? Plus 2az. Do you agree with this?
Yeah.
Okay. All right. What's the unit vector going to be? Well, it's rho vector over magnitude of rho. So that's going to be 2ax plus 2ay divided by what? 2 squared plus 2 squared, right?
You mean 2AX plus 2AZ?
Az, you're right. You got me on that one. Az, you're right. Y'all with me? Okay. So that's really what? Well, I can pull out 2 squared here. I get 2 over 2, 2, 2. I get square root of 2. So it's really what? 1 over square root of 2, and it's ax plus az. Az. Y'all agree with that?
Yeah.
Okay. Hang on. All right. So the rho value is just down here. It's got to be magnitude. This is going to be square root of 2 squared plus 2 squared, right? Or 2 square root of 2. And what is the A phi going to be? Well, remember, what is A phi? It's equal to AI, right? Crossed into A rho. So AI is just AY. Do you agree with that?
Yeah.
Crossed into A rho. A rho is this, so it's going to be AX plus AZ over square root of 2. So that means A phi, and it's in Cartesian coordinates because A phi, it kind of loses meaning unless I define phi. So I'm putting it in terms of X and Y. We could define phi and put it in terms of A phi at an angle phi equals this, but this is easier. So I have 1 over the square root of 2 And then what's AY crossed AX? Right, minus AZ.
Minus AZ.
My AY crossed AZ is plus AX, correct?
Yeah.
All right, now, if you look at that's exactly how it would be pointing. Minus AZ plus AX, if you actually draw that. Right here, it's pointing this way. This is the H field right there. I'm trying to just show you that. You all with me?
Yeah.
It's important to know this. It doesn't come out really that well in the book, I don't think, but that's a real important concept to have an appreciation for. All right, next. We go till 2:30. Good. Give me 1 second. I'm curious about one thing. I'm in Auburn. Is anybody else here on this chat on Auburn? No? Chase, are you here or not?
Yes, sir. I'm from Auburn.
I'm not.
Are you in the Carolinas right now?
Yeah, I am.
I don't know where the rest of these guys are, but we had some bad weather yesterday here. I think we're going to get more. I don't know what the Carolinas. Where are you, Zach?
I'm down in Florida,
What part of Florida again?
right next to Panama City Beach.
All right, you told me that. So you didn't get any bad weather. You've been
No,
lucky.
sir.
I figure you get worse weather than us, but we got. And I think today we're going to get some more bad weather. The rest of the people, I don't know where they're at, but this is the time of year where tornadoes make my life miserable. So anyway, so I went through those two things. Can anybody guess how you? This is going to be in your book, and I think it's figure 413, but I don't know because I don't have that. That book, unfortunately, is at the office. I'm using my old book. Do you see something that's a solenoid? It's just a whole lot of loops of wire. Let me show you what I'm talking about.
Yeah, that is 413. That is 413.
All right, now I just want you to understand this. Whenever you have these kind of problems, it's a building block approach. You see how if you just take a sliver up at a point and have a thickness dz, that looks like a loop of current, right? Just think about it. Solenoids, just the coils and coils of wire. Well, that loop of current right there can be thought of as creating a differential H field. We found the actual H field, but it could be a differential H field from that. But here's what I mean by that. If you have a whole lot of turns of wire, and we just look at a couple of turns with a height, with a thickness dz. Suppose I do this. I'm going to say I got a loop of wire here. And now the current on there is di, and di is actually equal to the current density, that be amps per meter in terms of the turns rate. Now just call it K times dz. This is going to be the z direction. So I have this loop, and this is di, which is likened to I before. If you think about this, remember the actual H field was equal to I right here over 2 pi magnitude of rho in the A phi direction, right? Now what we do is say this. Assume this thing doesn't
Wait,
have.
that's the H field for a that's an H field for the infinite wire, right?
I'm sorry. This is AZ. My bad. You're right. You're gonna see it looks the same. So I'm sorry. My bad. The H field. I'm glad you were paying attention. Is equal to I. My bad. Over, and it's going to be 2. This one, I don't know where it is in your book. Let me see this. I wish I had my board with me. I think it's equation 4.9. So it's I a squared over here. It's h squared plus a squared. Instead of that, I'm going to call it z minus z prime squared. I'll explain this in a second. Plus a squared, and this is going to be to the 3/2 power az. that was the H field from a given loop, but I put Z minus Z prime because what I'm going to say is we want the location of the H field on the Z axis, but this is going to be assumed at Z prime. So the difference in Z from here to here, delta Z, or the height difference, is going to be Z minus Z prime. And it doesn't matter if you have Z first and Z prime second, but the reason I'm doing that is because this is going to be a differential amount of H field instead of an actual H field. And the I there is going to be replaced by DI, which would be K times DZ. Now, this is getting a little hairy, I know that, but I'm trying to say that I'm going to assume I figured out for a single loop of current what the H field was as height Z. So I'm going to use that thing as a building block and say that now I can say, well, if I know the differential current from a single loop, suppose that's a differential amount of current there, what is the differential H field it causes here? And it's the same thing as the I in a single loop causing an H, only now the current itself will not be equal to I, it will be equal to DI, or it's really the amount of current per meter times the differential thickness. And that's what he's showing you here. And I'll get to that in a second. As a matter of fact, let me blow that up just a minute. And I'll talk about this. So I can do it this way and you'll appreciate it more. Here's what we accomplished last time. I mean, we said that this is the H field. Can you all see this right here where the cursor is? Or not?
Yeah, I can.
Kind of small. What in the world is causing all that flicker? I don't know. I'm gonna just leave it. It's on my end, not yours. But anyway, if you look here, there's nothing moving, it's flickering. Anyway, if you look here and you make I DI and this DH, and instead of H, you put Z minus Z prime, because that's the difference in the height from where this differential current would be creating the H field to the point of observation, the Z direction. If you do that, you get this. Just take a look for a second right here. Here, first of all, DI. What he's saying here for DI is you've got N turns of wire over a length H. So this has a height H, but it has N turns. So how much current's flowing around azimuthally? It would be N times H. That should make sense. N times H would be the amount of current, and that means the current density that's circulating would be N times H, or I should say N is circulating around there times I. If you divide that by H, you get the differential current per Z or per DZ. So if you take DI DZ, it would be N over H times I. Therefore, if you want differential current, it's NI DZ, and that he puts this in here, NI DZ. Then he's got the A squared in there over 2. And here, H, he took this H and put it down here. That's not the height, it's the actual, it's the height of the actual coil. And then he has Z prime squared, or Z prime squared plus A squared, where Z prime is just going to be the measurement from the point where the actual differential current element is to the point of observation. Now he makes the other value of Z 0, so he wants the actual H field right at the center. He goes through and he gets this integration. And when you do it, you end up with this right here. Now, in your book, it'll be 411, I think. Take a look. Can you all see that in your book?
Yeah,
Here's the important part about this. Now, that is the differential H field for any height Z. Actually, I say he put it at Z. Actually, he did a variable transform there, but this is for any height at Z. Now, when Z itself, when you take a look at this thing, as the thing gets very long and narrow, so that basically you have H going, if you take it at Z equals 0, which gets rid of this term, and you take it as H gets large, you'll find that the H field, the center of the solenoid is this. This is Ni over H, that's dead center, and that's a very, very good approximation. If you know, most coils have a ton of turns over a short distance, and they're relatively thin. These are inductor coils, and I got a story about this too, by the way. If you take a look at that, that'll give you a very good approximation of the H field, the center of that coil. There's a lot of reasons why you want that, and I'll give you one that I have personal experience with. This is kind of interesting. So, how many know what a coil gun is? Have you ever heard of that? Or rail gun, but coil gun in particular. Anybody?
I've only heard of a railgun.
A coil gun is based on similar principles. It's using electromagnetic force to thrust something out. So if you just think of something about the size of the core on a roll of toilet papers, or maybe paper towels. So you got something that long, maybe a foot long, and you wind it with maybe 1,000 turns, maybe 10,000 turns of wire. And then you put current through it. It's going to have a magnetic field that's given by this at the center, and it's got a peak value at the center. As you get towards the ends of this, and we can prove that, the ends of the coils, the H field is about 1/2 the value at the center, about. But here's the one thing about that H field. It's in the Z direction. You all follow me on that, class? It's down the axis. Now, if you take now, we haven't gotten to magnetism, magnetic forces and stuff, that comes later. But if you take something that's a ferrite or a magnet and you introduce it to the end of that thing, it will be pulled to the center of that thing, and it will just oscillate and bang back and forth until it comes to rest in the center. This is assuming a strong magnetic field. Does this make sense to everybody? You know what magnets are, right?
Yeah.
All right, well, now here's the deal. With a coil gun, you energize the coil and let the ferrite piece of material, magnet, go, and it's going to accelerate towards the center, and then you quench the current, so the magnetic field's going to 0 before it hits the center, and it just launches the thing. My first experience with something like this was a graduate student in textile, or well, in whatever it's called, fiber and polymer engineering, wanted to actually create a coil gun like that would launch. It's called a shuttle, I think, for a loom that weaves things. So you shoot string through it, then the loom closes. Basically, it's got fabric on either side, and then grab it and shoot it back through. You don't know what these things are. You've seen them, right? They're the old way of doing weaving or creating fabric. Anyway, so he wanted to do it, and they needed some help, so they asked me to help him. So we designed this gun, and he used the cameras, the old cameras, the Kodak cameras and stuff that have flash, bulb flash. So he got some of these and some capacitors, and this is just the step-up transformers. And he got a battery, and he charged up a bunch of capacitors. They were real small. We figured out about how much energy he's going to be able to store and how much the percentage that he could get in the nail. It's very small. It's only 5 to 10%, not even that. And he used the nail for his ferrite. So he was upstairs. I thought this thing was just going to come out and fall to the floor. I didn't have a lot of hope in this because it wasn't it didn't impress me at the size. It's super small, and it's got a capacitor. It's got a DC battery, and I'm thinking, well, it'll be interesting to see what happens. So I'm going to go ahead and do it. I didn't hear anything except the nail hit the side of the wall on the opposite side of the room and just ping. I'm thinking, this is low power. No, I mean, no sound at all. Absolutely silent. If this is subsonic, this is the perfect assassin's weapon. It is like a 300 blackout with a silencer, only much quieter. It was unreal. And this kid, so long story short, the real problem with this is not getting this projectile to move. So he's going through in his brain thing, but he wanted to catch, you got to catch the thing, and then you got to load it into another thing with that weave. Remember, there's string there, so there's some way for this thing to load and that tangle and fire it back. And that was the problem. He never did figure out how to do that. And I wasn't going to play around with it anymore because I could see I can get some real trouble if this kid starts shooting people with it. And anyway, he did get his master's with it, but he never did produce something that was used by the textile industry. That was my first experience with a coil gun. Since then, students have been fascinated with coil guns and rail guns, and YouTube has all this information on how to make them, but it's based on a solenoid. That's my story. They tell us that it helps students retain information if you can liken it to something in the real world. Don't make a weapon. That's my one piece of advice. Don't make something that's going to shoot, squirrels or people or something like that. You'll end up in trouble somehow down the road. I just have this gut feel. But I did see one last thing I'll tell you about. I saw somebody marketing, I'm not joking, a real, like a battery operated handheld railgun. That's not the thing you really want to do, but it's probably for display. Okay, good enough with that, guys. Appreciate you indulging me. So the next thing after this, and I'll give you problems on this. You'll realize this is very similar to what you've been taught in physics, right?
Yeah.
I mean, it's literally identical to physics, except with a little more, I guess, complexity of problems. But the theory is the same. So now, what if we have an infinite line charge? And I'm just going to show you this is in the book. And here, I mean, infinite, pardon me, sheet of charge. This in my book is figure 314. In yours, it'll be figure 414. Can you all see that for a second?
Yeah, but it seems it's a ribbon, right?
Mm-hmm. Call it a ribbon. It's a sheet. It's just a flat, thin piece of conductor where there's a certain amount of current per meter flowing in the same direction. Y'all follow me on this, guys?
Yeah.
Now, most of you can see that what this looks like is just a whole bunch of thin wires that are causing the current, right? Y'all follow me? So what they're going to do is this, and I'll tell you how they do it. The only thing they do is say, well, we're going to make this a very thin wire, all right, or a thin ribbon, whatever you want to call it, of some, let's see, it's going to have a dx width in my drawing. So it's going to be dx times kz, and kz would be the current per meter flowing in the z-axis. Do y'all follow me? So if you had 20 amps per meter flowing up, that times dx would be the amount flowing in that thin sliver that's infinitely long. Makes sense to everybody? All right.
Yeah.
Now I got to find the H field at this point. So I'm here at some point here, and I need to find the H field where I'm A away. Here's where I move over to this thing. Now this is looking right down the z-axis. Take a look. We're at a distance y. Here's my differential current. Is this
Yeah, it's right next to it.
414? It's next to 414.
Yeah.
All right, I think it's 414. All right. Well, right there, we've got, instead of having I over, or I a squared over 2a squared plus z squared, all that crap over 2 pi. Now I'm saying I over 2 pi rho, and then it's going to be a phi. Instead of that, we're going to make it differential. And in his book, he does this. I'm going to show you this. What is that dang thing? if you look here, that's DH from an infinite line of current right here. And I think y'all can see that. So if I go ahead and make this DI or this I here a differential where, wait a second. Yeah, he does have DH here, but I here is going to be equal to KZ times DX. And then A phi has to be defined by DI or AI, unit vector in the I direction, crossed into a unit vector in the rho direction. He does it right here. And this is, it should be in that section, but you can see here he has KZ and DX. So that's the differential amount of current. Then he has AZ, that's the differential current. I mean, the AI is a unit vector in the direction of current crossed into, and here would be the actual, this is into the actual radius vector. So this will be A phi. It's minus X AX plus Y AY. He's going to get this, and then he does the integral. I'm sorry, I'm not in front of you guys to do this on the board. It'd be a lot easier for me. Let me see if I can blow that up. So that's what he's doing here. And if you take a look at this, this is how he's getting that information. There's A phi, it's AZ cross AR. And that's what he has inside of here. And when you, here's the integration that needs to be done. Now, something I'm going to mention about this. I hope you can see this. I know it's not exact, but can you all follow me on why I'm doing what I'm doing? I can do this on the board for you.
Yeah.
If you just look at this, it'll make perfect sense. Once you get the differential H field from this current in the Z direction. So this differential H field caused here, you get it integrated over the actual width of the ribbon. He's got it going from minus D to plus D. You get this value if you do that integration. I'm just going to tell you, it's a very doable integration. And this part cancels. So you're going to get something only in the AX direction. Now, one of the things I want you to note about this, you can star that one here, but the thing to note, as the width of that ribbon goes to infinity, this is the H field you're going to get. And I'm going to show you a trick with this one. Can everybody follow me on this? One of the things you'll notice is the H field is not a function of position. It's only really a function of the side of the sheet you're on. Remember, if we had an infinite plane of charge, do y'all remember if you had an infinite plane of charge, the D field or E field was a constant. The only thing that mattered was a direction. If you were above the plane, it was pointing upward if it's positive charge. If you're below, it's pointing the other way. It's always pointing away from the charge if it's positive charge. Y'all remember this class?
Yeah.
For this one, it's a surface current. Now, if you think about this, try to just follow me on this. I want to make this point. If you have a surface current, here's Z, and I'm going to assume that the surface current is in this direction. So I'm going to have a surface current density K and say it's 5 amps per meter. And that's going in the A, because that's X, this is Y, in the A, Y direction. Can you all follow me on this?
Yeah.
All right, so if I am above, if I'm above or in the positive Z direction at any height, the H field itself right here in magnitude will just be I over 2. And I don't know where he does this in the book, or I shouldn't say I, K, pardon. It would be, if I'm above it, the H field would be equal to K, which is down here, amps per meter over 2. And here's how you get the direction. technically speaking, it's just, if you have this, it's a unit vector in the direction of the current. So this direction here would be unit vector in the direction of current AI crossed into A normal. Now normal is always pointing radially away from the current, surface current, and it's from the minimal distance to the point of observation. So if you look at this above it, AI is in the Y direction, AY, crossed into AN is AZ. So Y cross Z is AX. If you take a look at this. So the differential H field here above it, I'm sorry, not differential. The actual H field there above it would be equal to K down here, 5 amps, over 2 AX. What if I'm below it? Suppose I'm below this, and I want to know what the differential H field is, or the H field, pardon me. It'll have the same magnitude. It's going to be K over 2, but the direction, the normal is now minus AZ. So minus AZ, this is going to be AY times minus AZ is going to be this direction. So it's going to be minus AX. I'm not saying it's quite as well as I'd like to, but y'all follow me on this class? And here's how you really get it. You got a right hand, correct? Put your thumb in the direction of current where the current exists and see how your fingers curl. If you're above the infinite sheet, your fingers on your right hand will point in the direction that the H field is going. But remember, it will always be perpendicular to the normal vector and to the actual unit vector in the direction of current. So here it's going to be positive AX. Do it. If you're, move that, reduce that zoom. Sorry. If you're above it, right, it's going to be in the positive X direction. If you're below it, in the minus X. Just take a second to look at that. Y'all see what I'm talking about here, class?
Yeah.
Do y'all remember this in physics? I don't know if they went through all this or not.
Some of it.
That's the easy way to do that. And now, typically, yeah, you could have a finite ribbon where you'd want the H field. You need to know how to do it. But more commonly, they assume infinite sheets. Here's where it became really valuable to me. Years ago, back in 91, I think, no, 1990, I was working in the summer as a consultant to the to MISIC. Really, it was at this EMP, or it was really a electromagnetic environment group up in Huntsville, and I was working with Jim Now and some of these guys that did lightning protection work, and they had this thing called a multiple launch rocket system, and they needed it to test it to see what lightning would do to it. We had this grid that we charge up with we had capacitors that were enormous. We could get a couple million volts, and we had a wire grid, and it was about 20 or 30 feet high. And under there, we put this multiple launch rocket system. And where we wanted this pseudo lightning to attach when you charge it up the capacitor, we put a paper clip on the thing and then bend up one end, tape it to it, and the lightning would hit that point all the time. And then we could measure the actual induced currents using B dot probes. But here's something. A lot of times you had surfaces that would have a flat, like be very flat, and currents flowing down there, uniformly distributed on the surface over something that looked like an infinite length. And we could estimate what the actual current would be by measuring the B field right above that surface. So here's the deal. You got an infinite, like a sheet, and then right above the sheet of charge, or sheet of current, where the current's actually flowing, and you can assume for a lot of reasons the current's going to be planar, and we could get the current density by just measuring the H field above it. And we did it with something called a B dot probe, and that comes later. But we could use the assumption that the B field just above there was really equal, or H field was just equal to the current surface current density divided by 2, and it worked like a charm. So we did a lot of stuff like that. That's and I'll have to show you more about this in class next time. So That's some experience. Now, what I'm going to do is this. There's no quiz today. I mean, Wednesday. I'll give you a quiz on Friday, but in class on Wednesday, I'm going to go through all the theory. I'm going to show you this. I'm going to give you some homework to do. Please do that. All right. And Zach, you're going to have 2 quizzes, and I think a few of the other people are too. We've got at least one more that's in both my classes. Are you all with me on this class?
Yeah,
Now, it's straightforward stuff, but please keep up with it because it can get, I'm going to go over some new material on Wednesday, but it can get real confusing. That camera was straightened out, by the way, thankfully. Any questions at all? Because I think it's about done.
I'm good.
By the way, have a great 4th of July celebration. I think there's fireworks here at Duck Sanford. Is that right, Chase?
Yes, sir.
Tomorrow, it's